How often do you really stop and think about what happens to rain after it hits the ground? You might picture, a simple drain, maybe a gurgle, and then it's gone. But trust me, the world of stormwater is far more complex and, dare I say, genuinely fascinating than you might imagine. Okay, let's unpack this. Today, we're taking a deep dive into this hidden world beneath our feet. We're pulling insights from a really comprehensive source, the Stormwater Collection Systems Design Handbook. And this isn't just about pipes and drains, is it? It's a surprising mix of engineering, ancient history, modern policy, even like human behavior.
Yeah, it really is. What's truly remarkable here is just the sheer breadth of things you have to consider when managing water. I mean, everything from a single raindrop up to a massive citywide flood. So our mission today is to pull out the most important nuggets of knowledge from this material. We'll trace the evolution from, some surprisingly ingenious ancient solutions all the way to cutting-edge computer models. We want to help you become genuinely well-informed on a topic that honestly touches everyone's daily life, often without us even realizing it.
Okay, so let's start by looking way back. You might think sophisticated drainage is purely a modern invention, but here's where it gets really interesting. Ancient civilizations were, well, incredibly advanced. We see clear examples like the drainage system at Knossos on Crete. Pretty intricate stuff. But maybe even more intriguing is Pompeii.
Oh, yeah, Pompeii is fascinating.
Right. Ironically, the older part of Pompeii was the only part of the city that had dedicated storm drains.
Isn't that something?
It is. And these weren't just simple ditches. They were quite robust for their time, designed to carry water away, often running under sidewalks or roadways. They even had manholes with stone lids for inspection and maintenance. It really shows some serious foresight.
That ancient ingenuity really stands out, especially because for a long time after that, we actually lacked systematic ways to measure things like rainfall or water flow. And frankly, spending on storm sewers just wasn't a top priority compared to, say, other public works. But by the mid-1950s, engineers really started to recognize the limitations of the simpler, rational methods they'd been using to predict water flow. That was a pivotal moment. It prompted this urgent need for more comprehensive, more scientific approaches.
Okay.
And that's when we saw the first real hydrological models emerge. Things like the Road Research Laboratory, or RRL model in the UK, and the Chicago model here in the US. This period really kicked off a rapid sort of proliferation of models across the US. You had systems developed by the EPA, the University of Cincinnati, MIT, others too. This wasn't just a technical upgrade, it was a profound shift. Moving from managing water with intuition, maybe, to doing it with scientific precision, really protecting communities on a much larger scale.
So given all that history, how do we manage stormwater today?
Yeah.
Because it's definitely not just an engineering challenge anymore. It's heavily regulated, lots of rules.
Oh,
And
absolutely.
take floodplain protection, for instance. A flood hazard area that's typically defined as the 100-year floodplain.
Meaning a 1% chance of flooding in any given year.
Exactly. And within that, you have the floodway. That's basically the path the deepest, fastest water would take during a flood. Now, the National Flood Insurance Program, the NFIP, has this crucial requirement. Any new development in these areas cannot cumulatively increase the water surface by more than 1 foot.
Which is a really important constraint.
It is. The core idea here is that floodplains aren't just empty land. They act as natural conveyance channels and critically temporary storage areas for excess water. If you allow obstructions, like buildings or even, say, detention basins in these floodways, you're essentially blocking that natural storage.
Right. And that just increases water levels both upstream and downstream. It can make floods worse for everyone.
Precisely.
And this naturally brings up another critical question. What about water quality? It's not just about the quantity of water anymore.
Good point.
The EPA, for example, mandates that water quality standards must support fishable, swimmable uses, unless, those uses are demonstrably unattainable for some reason. And to figure this out, scientists perform something called Total Maximum Daily Load Studies, or TMDLs.
TMDLs.
Think of a TMDL as basically a pollution budget for a water body. It determines the absolute maximum amount of a specific pollutant, like sediment or nitrogen, that can enter the water without violating its quality standards. If these studies show that too much of something is flowing into a stream, then any discharge permit within that system might need to be revised.
So it forces facilities to clean up their act.
Exactly. It forces them to lower their pollutant levels to meet that TMDL budget. It's a direct link between the science and real-world environmental action.
And these rules definitely extend to permits and some pretty hefty penalties, too.
They certainly do.
Generally, if you're doing any construction that disturbs more than 5 acres, that's about 2 hectares, you'll likely need a stormwater discharge permit. And that's regardless of how much rain is expected.
Right, the disturbance itself is the trigger.
Exactly. Now, there are some exceptions for smaller projects if the soil isn't likely to wash away easily, what they call low rainfall erosivity. But even industrial facilities need a permit if materials, equipment, or products are exposed to stormwater.
Like those oil drums you mentioned.
Right. Imagine oil drums during loading.
Mm.
If there's any reasonable potential for leaks or spills to get rained on, that area needs a permit.
Yeah.
And the cost of not complying, wow, it can be truly substantial.
We're talking serious money.
Yeah. Penalties can be up to $11,000 per day, with a maximum around $137,500. And civil penalties can go even higher, up to $27,500 per day for each violation.
Per violation, per day.
Per day, and that accrues daily, with a 5-year statute of limitations.
Oof.
These eye-watering penalties aren't just about punishment, right? They really underscore society's commitment to protecting the environment and public safety. It makes it clear that managing stormwater responsibly isn't optional. It's an economic imperative. Okay, let's dive into some of the nitty-gritty science now. To really tackle these challenges, engineers first had to understand the fundamental physics of how water moves.
Back to basics.
Exactly. And that's where the real scientific deep dive begins. Engineers use specific terms. For example, stage. That's simply the elevation of the water surface, like, a high water mark on a riverbank. They also talk about steady flow, where things don't change over time, versus unsteady flow, where they do, like during a flash flood.
Makes sense.
And uniform flow, that describes water moving at a consistent depth and speed. Now, a really popular equation for estimating how fast water flows in a pipe or channel under these uniform conditions is Manning's equation.
Yes, Manning's and...
Right. What's crucial to get about this equation is that the N value, that roughness coefficient, it isn't constant. It depends on how rough the surface is.
Like sandpaper versus glass.
Exactly. Think about it. Water flows much slower through a corrugated metal storm drain that has a higher in value than through a smooth concrete culvert, which is way more efficient. And sometimes you get something called a hydraulic jump.
Those look dramatic.
They do. Imagine water rushing down a steep slope really fast, supercritical flow, then suddenly hitting a slower, deeper pool, subcritical flow. That abrupt, often turbulent transition, that's a hydraulic jump.
And engineers can actually use those.
Yeah, they often use structures like weirs or sills to intentionally force or control these jumps. They use them to dissipate energy safely and prevent erosion downstream.
Interesting. So that understanding of the physics leads directly to predicting how much water moves and when, right?
Precisely.
A key concept here is time of concentration, usually abbreviated as etc.
Okay, etc.
It's essentially the time it takes for a raindrop falling at the furthest point of a drainage basin to flow all the way down to the outlet, like the mouth of the basin.
So, like a travel time for the water.
Exactly, a travel time or lag time. Now, precisely calculating TELA involves some pretty complex hydraulic analysis using things like the SWMM equations we'll touch on later. But for practical estimation, engineers often use empirical formulas. And interestingly, these different estimation methods tend to agree more closely for smaller basins.
Okay.
Now, for figuring out how much runoff to expect, especially in smaller drainage areas, say less than about 80 hectares or 200 acres, the rational method is very commonly used.
The rational method. Sounds simple.
It operates on a fairly simple but powerful assumption.
Right.
Basically, that the maximum runoff happens when the entire watershed area is contributing flow simultaneously, and that the rainfall is uniform over that whole area.
Makes sense for smaller areas.
It does. And when designing structures like pipes or culverts, engineers also consider design frequencies or return periods. This means planning for how often a certain intensity of storm might occur.
Right, like a 10-year storm or a 100-year storm.
Exactly. So a culvert under a low-traffic road might be designed just for a 5 or 10-year storm. But critical storm sewers in a large city, those might need to handle a 25 or even a 50-year event.
Much higher stakes.
Much higher. And critical tools for understanding and modeling these rainfall patterns include IDF curves, that's intensity, duration, frequency, and design hydrographs, which basically show how rainfall intensity changes over the course of a single storm event.
Got it. So with all that science, the physics, the predictions engineers, then design these, well, truly incredible solutions to actually manage the stormwater.
Right, putting the theory into practice.
A common one you might see, but maybe not realize its full purpose, is a detention basin.
Yep.
Looks like a pond, sometimes dry. Their main job is to reduce the peak flow rates during a storm. They hold water back temporarily, releasing it slowly to prevent those sudden, damaging surges downstream. Their design relies on these crucial relationships: stage storage, how much water it holds at different depths, and stage discharge, how quickly it lets water out.
And then there are the extended detention basins.
Right, those are a bit different. They have a dual role, which is even more important for the environment.
The water quality aspect.
Exactly. Their lower part, the bottom stage, is specifically designed to hold back a certain amount of runoff, often called the water quality volume, for an extended period, maybe 24 hours, maybe more.
Allowing pollutants to settle out.
Precisely. It allows pollutants like sediment and associated contaminants to settle out or be treated biologically before the cleaner water is slowly released. Hugely important for downstream water quality.
There's an example from Hampton Roads, Virginia, requiring that first half-inch of runoff from impervious areas to be released over 30 hours.
30 hours, yeah. That
Huh.
really slows down. But these basins aren't perfect, right? They have challenges.
Oh, definitely. Clogging is a massive issue.
Right. Those graded structures and the small low-flow outlets are really prone to getting blocked by trash, leaves, sediment.
Which can lead to all sorts of problems. Soggy bottoms, dead vegetation, slippery slopes, even safety hazards if water stays ponded too long.
So while things like debris racks can help a bit,
There's really no substitute for regular maintenance inspections. Someone needs to physically check and clean them out.
absolutely crucial. And engineers also have to think about groundwater, right?
Yes. If a basin is meant to be a dry pond, maybe used as a park or a sports field between storms, it absolutely needs to drain completely. But for wet ponds, the ones that hold water permanently, you have to assess how water might seep into the ground, infiltration, or how groundwater might seep into the pond, exfiltration. That interaction with the water table is critical for how they function long term.
Makes sense. Okay, so beyond basins, what about the pipes and channels themselves? That must involve some complex science, too.
It does. For analyzing unsteady flow in sewer systems, remember, that's the flow that changes rapidly during a storm. Engineers use sophisticated models based on these Semphenol equations. These are basically the fundamental equations governing open channel flow.
Okay, self-and-on. Sounds complicated.
They can be. And to make modeling pressurized pipe flow a bit easier, especially when pipes get full and surcharge, they even use this clever conceptual trick called the Priceman hypothetical slot concept.
A hypothetical slot.
Yeah, it sounds weird, but it effectively transforms a full pressurized pipe into a conceptual open channel flow by imagining this narrow virtual slot along the top. It just makes it easier to handle within standard open channel modeling software.
Huh. Clever workaround.
It is. And when you're talking about culverts and open channels, two really crucial concerns are sedimentation, where dirt and debris build up and scour.
Scour, that's erosion, right?
Exactly. The erosion of the streamed or banks, often caused by fast-moving water, especially around structures like bridges or culvert outlets.
So how do they prevent that?
Well, they use various structures, things like spurs, which are like little jetties that stick out to deflect water away from vulnerable banks, and guide banks, often shaped like a quarter of an ellipse, are used at bridge entrances to smoothly guide the flow and prevent erosion there.
And what about just general erosion control during construction? That seems critical, too.
Hugely critical. Honestly, the most effective thing is often just preserving existing vegetation where possible, or quickly revegetating disturbed soil. That alone can provide something like a six-fold reduction in suspended sediment levels.
Wow, six-fold.
Yeah, vegetation is powerful, but non-vegetative practices are important too. Things like degradable soil stabilization blankets. You see these sometimes. They look like mats laid on slopes. They protect seeds, help retain moisture, and physically prevent the topsoil from slouging off, especially on steeper slopes. And for temporary measures during construction, you'll often see things like stabilized construction entrances, basically gravel pads to knock mud off truck tires, and sandbag berms to divert small flows.
Right, okay. Now, here's where I think it gets really compelling for our daily lives.
Mm-hmm.
How urbanization, and especially our choices, like owning cars, have profoundly impacted stormwater.
Oh, absolutely. The footprint is huge.
The growing influence of the automobile, really taking off from the 1920s onwards, led to this massive surge in impervious surfaces. We're talking roads, parking lots, driveways, garages. Anywhere water can't soak into the ground.
Just acres and acres of it.
Get this, from 1915 to 1994, the U.S. population grew by about 2.6 times. Okay, significant growth.
Hmm?
But the number of automobiles, it grew by an astounding 80 times.
80 times. That's incredible.
It is. And it means much, much higher amounts of impervious surface per person. And critically, many of these surfaces are directly connected to drainage systems via curbs and gutters. Water just sheets off them straight into the pipes.
Which drastically increases the volume and speed of urban runoff.
Exactly. And here's a really counterintuitive point from the research. Low-density developments, the suburbs with big lots, they often have a greater impact per house in terms of both total impervious area and that directly connected impervious area.
Wait, how does that work? Bigger lots should mean more green space, right?
You'd think so, but it's largely down to the extensive street designs. Wide roads, long driveways, lots of curb and gutter needed to service those spread-out houses.
Yeah, the infrastructure footprint per unit is larger.
Precisely. But there's a potential solution kind of hiding in plain sight. Local streets. They make up nearly 70% of urban road mileage, but they only carry about 14% of the traffic.
Right, mostly residential traffic.
So these streets are prime candidates for rethinking the design. Maybe narrower pavements, maybe different drainage approaches, all aimed at reducing that impervious footprint.
That makes a lot of sense. And this whole shift in understanding the impacts of urbanization really leads to new approaches in management, doesn't it?
Definitely.
We're seeing this significant move towards small-scale distributed stormwater control. You hear different terms for it. Low-impact development, or LID, or best management practices, BMPs.
LID and BMPs, yeah.
The core idea is to spread smaller, decentralized systems throughout urban areas, rather than just relying on, one huge detention pond at the bottom of the hill.
So integrating solutions into the landscape itself.
Exactly. Things like porous pavement that lets rain soak right through, infiltration trenches or pipes that guide water into the ground, designing functional landscapes like rain gardens that naturally absorb and treat stormwater right where it falls. And we've even seen some really ingenious, maybe slightly unconventional solutions, like those implemented in Skokie and Wilmette, Illinois.
Oh, yeah. What do they do?
They successfully used what they called regulated surcharge on residential streets. Essentially, they designed the system to allow water to back up shallowly onto the street surface during really heavy rainfall.
On purpose. On the street.
On purpose, yes. But shallowly, maybe just curb height or slightly more, it dramatically reduced sewer overflows and basement flooding because the street itself became temporary storage.
Wow. How did residents react?
Well, it was designed carefully, shallow enough for slow-moving cars to still get through, and the ponding only lasted for a short, publicly acceptable time, and a kind of clever side benefit. These roadway modifications also acted as traffic calming devices during dry weather.
Huh. That is clever. Two birds with one stone.
Pretty neat, right?
It really is. And even something as seemingly simple as litter, that plays a role too, doesn't it?
It absolutely does. And littering habits, as you might expect, vary a lot globally due to cultural norms and regulations.
But there's this interesting bit about high-density, low-income urban settlements, something called the visible grid paradox.
Yeah, that's fascinating. Paradoxically, in these areas, having openly visible grids or grates over the catch basin entrances can actually be more effective at preventing blockages.
More effective? How?
Because residents can clearly see when the grate is blocked by litter, and since a blockage might directly cause their own homes or streets to flood, they're often incentivized to clear the litter themselves.
Ah, self-interest keeps the drains clear.
Pretty much. If the litter trap is hidden underground, or if a little bit of litter doesn't immediately affect local drainage, people are just less likely to intervene. Out of sight, out of mind.
Makes sense.
Yeah.
And are there specific devices designed just to catch litter?
Oh, yes. There are various types. The Handbook mentions one, the North Sydney Litter Control Device, or LCD. It uses a removable basket and an inclined trash rack inside the catch basin to capture debris.
Like a little filter basket?
Kind of. But it's important to note that for traps that don't use fine screens, they generally need pretty low flow velocities inside the trap to allow the litter to actually settle out and be captured effectively.
Okay, so all this complexity, the physics, the regulations, the urban impacts, the different solutions, it must require some powerful tools to manage it all.
Absolutely. Modern stormwater management relies heavily on sophisticated computer models to simulate how water will actually behave in these complex systems.
What kind of models are we talking about?
Well, there's widely used public domain software from the EPA called basins. For designing storm and sanitary sewers, there's software like HYDRA, which can even help engineers select the optimal pipe sizes and slopes for a system.
So it helps with the actual design choices.
Yes, but for really complex flow problems, like simulating the details of scour around a bridge pier, or figuring out how flow separates around sharp bends, or even accurately locating those hydraulic jumps we talked about, you need more advanced tools. The Surface Water Modeling System, or SMS, is a good example. It's a comprehensive two-dimensional model that can handle these really tricky hydraulic situations.
Two-dimensional, so it's looking at flow across an area, not just down a pipe.
Exactly. It provides a much more detailed picture. And these advanced models are critical because they allow engineers to properly account for risk and uncertainty in their designs.
Risk and uncertainty. How so?
While rainfall is inherently variable, material properties might not be perfectly known, construction isn't always perfect. The models help engineers run scenarios, test sensitivities, and ultimately design systems that are robust and reliable, even when things aren't exactly as expected. It's where the mathematical rigor really ensures safety and performance.
Right. So wrapping this all up, what does this really mean for you listening? We've journeyed from ancient Roman drains through the science of hydraulics, regulations, urban impacts, all the way to cutting-edge computer simulations. It seems pretty clear that stormwater management is this dynamic, essential, and often kind of unseen field that's constantly adapting to our changing world.
It really is. It's this constant interplay between surprisingly historical insights, fundamental scientific principles, and evolving societal needs like dealing with urbanization or improving water quality. What really stands out, I think, is that what seems like just simple rain hitting the ground is actually managed by an incredibly intricate system, a system designed fundamentally to protect public safety, ensure environmental health, and subtly shape the very fabric of our towns and cities.
So maybe the next time a storm rolls through, take a moment. Consider that unseen network beneath your feet, that complex interplay of history, science, and human ingenuity working hard, often silently, to protect our communities and our environment. And maybe ask yourself this: what other invisible systems impact your daily life that you might just take for granted?